Right. So hi, everyone. It's my pleasure to introduce Dr. Dirk Wulff. Dirk is a researcher at the Center of Cognitive and Decision Science at the University of Basel, Switzerland, and soon to be head of search and learning research area at MPI Berlin. Or aren't you, Dirk? Congratulations. Dirk investigates the cognitive underpinnings of human memory and decision-making using a pluralistic methodological approach involving experiments, computational modeling, and big data analytics and process tracing. Today is going to talk about the semantic accounts of personality and risk. So, Dirk, thank you so much for taking the time to come and speak with us.
Thank you so much for the introduction and the invitation. It's my pleasure to be here and tell you a little bit about my work. So let me try sharing my screen. Can you hear me all right?
Yeah.
Yep, very good. Cool. Oh, I think you see the wrong screen, right? Where's the, there's the swap button. Now you should be seeing the correct screen. Is that right? Yes. Yep. Cool.
I still see your presenter view.
Yeah.
How about this? Still?
Yeah.
Ah!
No.
Now it's different, but it's not the slideshow either.
Yeah, it's still presenter view.
Still presenter view. Well, I
Yeah.
don't know. I'm switching between the monitors on my computer.
So you can do the three dots that you can. Oh, is that the key?
Three dots on Zoom?
No. Well, I'm used to PowerPoint, so I can't really. Can be helpful.
If it's mirroring on different screens, maybe you can share the other screen.
Or you could just on the top right, the second button.
Yeah, there is a
to change the views.
That's what I tried and it didn't do anything. But let me try something else. I just share my full screen.
Okay.
So now you should be seeing.
Yeah.
Yes.
Yeah.
Do you see all of it, including the header?
Yeah.
Yes.
All right, then let's go with this. Cool. So my pleasure to tell you a little bit about two projects that I'm very excited about. And both of these projects sort of draw on a notion that's very important in a lot of my work, and that's the notion of a mental representation or a semantic representation. So the idea is that based on all of the experiences that we make in our lives, we build up some knowledge about the world, and that knowledge we can represent as, for instance, a network of words or a space of words. And this network can then be used to understand human behavior in all sorts of different tasks. In some of our work, this is sort of basic cognitive tasks, such as free associations or similarity ratings or verbal fluency. But today we'll be talking about how we can use this, this representation or different forms of this representations to understand risk and personality. And what will help me a lot is that based on sort of recent advances in machine learning and artificial intelligence, and also through sort of efforts by researchers to collect a lot of data, that there exist now excellent opportunities to try to estimate these semantic representations to a very high accuracy. And there are generally two approaches to do this. One is coming from what I call the ecology or the environment, and that will be using large amounts of digitized text. And the other route is using behavioral outputs of people, such as, for instance, free associations. So how does that look like? If we try to estimate such a representation from text, then we're using co-occurrences of words across really a very large amount of text. One popular source of text is the Common Crawl database, which consists of 40 terabytes of text. It's mostly web pages, and it's supposedly about 5 billion different web pages that are included in the Common Crawl. And then different kinds of algorithms that have been proposed will parse that text and try to, let's see, you don't see my cursor, do you? Huh?
No.
All right, then I'll try to do it with words. So these algorithms will pass through all of that text and try to figure out within often a window of 5 words, which words co-occur. And the idea is that co-occurrence within such windows reflects the meaning of the words. This is going back to this old notion that you can know a word by the company that it keeps. So you try to infer the meaning of a word by just all of the different neighbors within a large amount of text. And yeah, and these days we typically do this using neural networks. A little bit more on that later as well. And then the behavioral approach, the one that I will be using, is based on large data sets of free associations. So there's one particular a large project that I'm also part of. I'm running the German part of this. That's the Small World of Words project. And that's a project that aims to collect large amounts of free associations from a large number of people in more than a dozen different languages by now. The oldest Small World of Words projects are the Dutch and the English project, and they're very advanced by now. And the English project, for instance, now has a publicly available data set that includes associations of 84,000 participants, amounting to about 3.6 million associations. How does that look like? It's a public website that everybody can visit to participate. And then when you participate, you'll be presented with different words, for instance, the word Robert. And then people would just list the 3 words that would sort of naturally come to their mind, spontaneously come to their mind when they see that word. And then they type in these 3 words, and then they would be presented with the next cue. So from both of these data sources, with different kinds of algorithms, we can derive and then a semantic representation that often has this form, which we often then call also an embedding. And it's a form where the different units of language that we're interested in, oftentimes it's words, but it can also be sentences. And the first project that I want to talk about in a little bit will be dealing with sentences. These representations deliver for each of these lexical units a numeric vector that can be of length 300 or length 500. And that numeric vector is then taken as an abstract representation of the meaning of those words. None of these dimensions have any specific meaning. There are ways of trying to figure out what these meanings may be, but we do know that we can, through different computational approaches, we can use these embeddings to derive predictions in terms of, for instance, how similar people believe things, lexical units are, or we can also train models that use these embeddings to do stuff. So that's illustrated here. So we can use these embeddings, for instance, to derive relatedness. That's typically true prediction. So this is done without doing any training or any weighting of the different dimensions. We use the latings embeddings, figure out the angle or the correlation between the vectors of these lexical units, and use these then as a prediction of how related these lexical units are. So one could do that, for instance, to do some kind of clustering, as is illustrated here, or we can use these numbers as direct predictions of semantic relatedness judgments, of the sequences in verbal fluency tasks, et cetera, et cetera. And there's a massive amount of evidence by now that the relatedness that's derived from these abstract representations can predict human behavior in a very accurate way. By the way, feel free to interrupt me at any point if you have questions. I don't know how you typically do it, but I'm very willing to take questions in between. So that's one way these embeddings can be utilized. Another way is to just use them in as features in a predictive algorithm to predict something. So later on, we'll be talking about risk perception, and risk perception is often done on the level of words. So humans might be rating how risky they feel the word banana is, or the word atom is, or the word weapon is. And for each of these words, we can derive these latent representations. For instance, in 300 abstract dimensions, and then we can use these 300 abstract dimensions as inputs to a predictive algorithm to predict, something like risk perception or all sorts of other responses to words, or even to sentences or larger lexical units.
I have a question, Dirk. Are you referring to the embeddings from the algorithms, say like a fast text and all, or are you referring to the to what you just described as the behavioral one that you just
either one. So later on, we'll actually have a direct comparison of fast text, other text-based embeddings, and the ones based on free associations.
Yeah, exactly.
We can turn either data into such a latent representation with exactly the same properties, and then we can see which one actually contains more of the information that I'm interested in when I'm predicting something like risk perception.
Yeah, okay, thank you.
So what I want to do on the remainder of the time is talk about two projects that leverage sentence and word embeddings. In one project to better understand personality, and in another project to better understand and predict risk perception. So on to the personality project. So in this project, Rui, Marta, and I were interested in using language embeddings to maybe clean up a little bit the mess that is personality psychology. Obviously, personality psychology is still a very popular and also a very successful field, right? But there's also been sort of a lot of work that hasn't really been consolidated, and this slide is some evidence of that. This is a slide that lists all of the different personality dimensions that, or personality scales. And a scale is a collection of items that would be used to measure a particular aspect of human psychology. These are all of the scales that are included in one larger repository of personality items out there, which is IPIP, the International Personality Item Pool. And as you can see, it's a lot. There's a lot of different scales out there, of which many share the same label. So the same scale name. For instance, here on the top left, you see there's 4 different scales of achievement striving. These may be exactly the same scales. By exactly the same, I mean using exactly the same items, but they may actually also not use the same items, and therefore possibly measure a somewhat different thing than the other achievement striving scales are measuring, right? And achievement striving, you can see, is not the only ones. We got plenty of scales to measure gregariousness or orderliness or thrill-seeking, etc., right? And it's still an open question whether all of these scales really do measure that. All of these scales that have the same level really do measure the same thing. And reversely, you can ask whether scales that have different names, all right, and therefore supposedly measure different things might actually not measure the same thing. And in this project, we try to possibly clean this up by using sentence embeddings. So the idea here is that we use a method that provides us with an abstract embedding of lexical units. In this case, the lexical units in question are sentences or personality items. And then we use the abstract representations that we get for these different items in order to derive similarities between these different items. And with these similarities between the different items, then we can figure out whether we can accurately predict, for instance, the internal consistency of scales, or scale intercorrelations, or the structural fidelity of the different inventories that exist out there. And if the item embeddings are able to predict all of these things, then maybe we can use them to reduce the space of scales out there to a more minimal set of actually different personality scales. The model that I will be using for the slides that I have in this presentation is a deep averaging network. I use a sort of off-the-shelf method, a pre-trained embedding, or a pre-trained model that allows me to generate embeddings. And that pre-trained model is called the Universal Sentence Encoder. I don't know how familiar you are with deep neural networks. And I'm not sure whether to go into all of the details, but this is a network that is not so different from the first neural networks that were used to generate word-based embeddings. So I'm talking about Word2Vec or the more modern fast text embedding. The difference here is that this is a model architecture that can take larger lexical units. So we can pass through multiple words and an arbitrary number of words. And then the embeddings or the encoding of these words will be averaged. And then there's a bunch of hidden layers that allow the model to pick up then on the signal that's coming from the encoding layer, and basically transform it into then what might be the meaning of that sentence. Yeah, these networks are interesting because they're not at all as complex as the large class of very popular transformer models these days. But off the shelf, we found that this particular model is actually doing best in terms of accounting for all sorts of personality measures. That said, I'm actually currently running a transformer model on a server in Basel, where I'm training it to actual data based on item correlations from a large assessment. And I find that all of the results that I will show you now, they're improved by a significant amount if we give these models access to actual data. But I think it's also impressive to see that what these models can achieve off the shelf. So what I'm doing here is, again, I use that model to embed all of these different items. IPIP has 4,450 items. And then I can use the embeddings. In this case, these are vectors of length 512. I use them to derive similarities of these items according to the embedding. And then I can derive scale similarities. A scale, again, is sort of a collection of items that's supposed to measure the same thing. I can derive them simply by averaging the item similarities. All right, so on the next few slides, I will show you some results that demonstrate that these embeddings can really recover important aspects of human personality. This shows a prediction of actual internal consistency. The internal consistency of a scale effectively is just a function of the correlation of the items within a scale based on human judgments. And I'm predicting it based on the average similarity of the items in the scale, but then scale to the appropriate test length, because internal consistency increases monotonically as the test length increases. And if I do that, then I find that I can predict the internal consistency of a scale with a correlation of about 0.51. I've looked at structural fidelity. By structural fidelity, I mean that the correlation of an item to the scale that it belongs to should be higher than the correlation of that item to all of the other scales in the inventory. And what I show you here, or the metric that I show you here, is the average correlation of the items to its own scale relative to the most similar other scale in the same inventory. So if we see a value larger than 1, that means the item is actually assigned. So if you imagine we would be assigning items to scales based on the similarity to other items, then a value of 1 would mean here that we would be assigning items to the correct scale, so to the right pool of other items within that inventory. And as you can see that for all of these, for about 440 different scales in that IPIP set, we can recover the structure pretty well, right? We are above 1, so we do have an appropriate self-similarity of these items. Doesn't entirely work for everything, but I think that's something that we will be able to fix using the trained transformers. On the right-hand side, you also see a comparison to real data. So here I'm using a large-scale assessment of the NEO. The NEO is a popular Big 5 personality inventory with 300 items. And I performed the same analysis, but using the correlation between responses. And you can see these, the structural fidelity is a little bit better based on actual data, right? We also see that we're capturing the variance in the structural fidelity in real data, et cetera. And we're also, in general, pretty close to the structural fidelity in real data, predicting, again, entirely without access. I mean, these models have no access to actual data. This is entirely based on just semantic information. Yeah, and then, which obviously is what, which is most critical if we want to use these models to clean up the space of personality scales. We looked at how well we can predict divergent validity, that is, to what extent can we predict the correlations between different scales. And here I'm also using the NEO data. On the left-hand side, you see the unsigned correlations. So we can't really do signs with these models. We can only tell are 2 scales related or not, right? So we're looking at, we're comparing the unsigned correlations in the NEO and the predictions of the model, and they align pretty well. So here we have a correlation of 0.45. Based on the trained models, we're looking at correlations here that might be in excess of 0.8 in terms of, like, in true prediction, in predicting the intercorrelations of scales. Ezekiel, you had a question.
Yeah, I need some detail to understand better the results. So the definition of item here is the embedding representation of text snippets, or it's a combination of this plus the personality scores, or how is it defined?
Yeah, so the item is literally just the text. So okay. I like to go to parties, right? That might be an item used to measure extroversion. Okay. And then I would take that short sentence, feed it through the universal sentence encoder, and get 512 numbers out that would represent that small sentence. Most of these sentences are somewhere in the same ballpark in terms of length. So we're not talking about sentences that, or items that are multi-sentence, which I think, in particular with using these things off the shelf, is one factor in the high accuracy that these models achieve.
Okay, thanks.
Yep, please.
I have a question. If there's like a baseline measure to what you're doing, like, is there a less fancy method to compare it against?
Yeah, so I've also done this with word embeddings. So fast text, for instance, and fast text is also surprisingly good, but not as good. And I've used, there's a Psych-Methods paper, I think from last year, that uses LSA. LSA is sort of an much older method based on sort of more based on the word frequencies of the actual items. And yeah, and that doesn't work as well, not nearly as well, actually. So yeah, you can achieve a pretty good performance with word embeddings. but these modern sentence embeddings are a lot better, or noticeably better.
Thank you.
Is that what you had in mind in terms of baseline?
Yeah, something like that. So there's some noise.
Right. So yeah, we can use these methods to predict the correlations between scales, at least within the NEO, and the current performance is about at 0.54. And again, when we train these things, we achieve quite a bit higher numbers, suggesting that we can actually use these models, in particular then later on the trained models, in order to figure out what the structure of personality actually looks like. And the cool thing of these models is that they're infinitely generalizable, right? So I can run these analyses now on IPIP, but there are other databases of items and scales out there, or people may come up with new items and new scales, and all of these things can be evaluated readily using these models. Yeah, one thing we might do is try to map out personality then. So this is a visualization using UMAP, which is sort of a newer method to project a similarity structure into a 2D space, reflecting the similarity patterns in the data. And this is all of the 450 or so scales in the IPIP database. And what I've also done, I've clustered them using the Louvain method. And I mean, there's like 6 clusters. I mean, you could take these now as sort of the new personality dimensions if you wanted to. But what I find most important is that this really seems to work, right? So I've highlighted a few of the more frequent scales in there, or scale labels in there, right? So all of the different intellect, aesthetic appreciation, gregariousness, and you can really see how they're ordered according to the label. But you can also see that some of them, for instance, creativity, right? They seem to be, the creativity scales, they seem to be in 2 different places. And that might be a point where we actually have creativity scales that might not be measuring exactly the same thing, right? And there's a few other examples. And that's something we can try to do also a bit more systematic, using a very interesting extension of this idea, and that is to use these language embeddings to not only embed the different items, but to also embed definitions of the different items and the different scales, but also use them to embed the definitions that we have of these scales. So what I've done here, I went to the APA dictionary and looked up the definitions of things like extroversion, neuroticism, intellect, etc. And since this is all based on text, we can put these in the same space, and we can now ask, is the definition, is the mapping between the scales and the definitions actually the best possible one that exists there? Or are there maybe scales where the items are very similar, but the definitions are very different, or the other way around? And that gives us a way to figure out, scales that could use a different labeling. Here's one analysis focusing on this notion of jingle-jangle fallacies, which is this idea that you have things that measure the same, well, that supposedly measure the same thing, but actually different things, or things that supposedly measure different things, but actually measure the same things. Here on the left-hand side, we have scales that where the scales are really similar. So this is based on the items. So the items of quickness and need for cognition are really similar based on the text model, but the labels, including the APA definitions of these labels, are really not so similar, right? And there's a few other ones for which that's also true. So in the middle, you also see the corresponding data, right? So these are all, everything we see on the left-hand side are cases where we have a really high similarity of the items, but a really low similarity of the corresponding labels and definitions. And on the other hand, we have a bunch of scales where that are labeled exactly the same way. Impulse control, I mean, there's multiple of those, or dutifulness, etc., that actually have a surprisingly low similarity of the items, right? And these are really candidates now for relabeling, right? On the left-hand side, we should be finding labels that match both of these sets of items. On the right-hand side, we should be finding new labels that match the differences in items. Yeah,
Sorry,
and there's also
sorry.
yes.
I need some help reading this graph. I'm still not quite with you. So on the left, you are doing what exactly? What does it mean? Similarity of scale with similarity.
Yeah. Yeah, so yeah, maybe that's not the best, is really maybe not the best name, but the similarity of scale means the semantic similarity of the items in the respective scales. Yeah, so this will be, yeah, this will be a quickness and need for cognition. That will be pretty much the average similarity of the items of the respective scales.
Oh, so these are pairs. These are all pairs.
Yeah. Sorry. Yeah, these are pairs of scales. Right. And on the left-hand side, we see pairs of scales where the items are really similar.
Yes.
But the corresponding labels that were given to these sets of items are actually pretty unsimilar.
And so give me an example of a label. Maybe that's what I don't understand.
So by label, I mean, for instance, quickness or need for cognition, or distrust, right? So basically these names that we have been given to these sets of items, and these names, I mean, supposedly reflect the construct that these sets of items are measuring.
Okay, so, but then you're operating at two different levels of embedding, because for the items, you're taking the entire item and convert that into an embedding, which is then correlated with the other items.
Yes.
Correct? And for the labels, that's generally just a single word.
Yeah, so it would be, but what I'm doing here is I'm enriching that text using the corresponding definitions from the APA dictionary.
Okay, fine. Okay. So now, fine, I understand what's going on now. So I see, and because you're using the definitions, it becomes more meaningful, because if the items are all the same, like for quickness and need for cognition, if the items are incredibly similar, then it is weird that they're measuring constructs that are far apart from each other, right? Is that sort of the conclusion?
Yeah, exactly. That's the point. So these are now, yeah, these sets of items need new names that would reflect the similarities. So we could call them both quickness, or both need for cognition, or something in between.
Okay. Yes, thank you.
And yeah, and interestingly, we can actually make these choices of which names to assign to these scales using the embeddings again, right? So we can take a set of items and then ask, what's the label and definition that's closest to that set of items? And by doing that, we can relabel all of the different scales. And we can also ask how many different constructs or labels and definition do we actually need to appropriately capture the entire space of item sets out there. And this is what this analysis is showing. So on the x-axis, you have the number of different, I call it constructs here, but it's basically labels plus definitions, right? So the number of different labels plus definitions that are made available to the analysis in order to optimize the mapping between these constructs, right, and the different items, item sets, right? And you can see that if you only give it one construct, then we're not as good as if we give it a maximum number of different constructs to use to do that optimal mapping. And what's interesting here is that obviously we can determine the current similarity between the existing labels plus definition and the item set, and that's that dashed line there in the middle, right? And then we can ask how many constructs do we need to maybe exceed that existing similarity. And this analysis shows 4. So by using 4 labels plus APA definitions, we can exceed the similarity of the existing set. Right? One should now conclude that really 4 constructs are enough, right? This is obviously not perfect. Earlier, I showed you that there's only a correlation of 0.5 in predicting scale similarities. Nevertheless, it gives you an idea that maybe we can do with a considerably smaller number of different constructs. And what I show you on the next slide is maybe a reasonable estimate. So I looked at where this sort of curve is maybe having its bent, a little bit like the elbow test in factor analysis, and that might be at about 15, and that will be the relabeling using 15 labels. So on the top, you see the labels that were assigned to the different scales that are presented below in a word cloud, right? And these are the labels that were originally given to the scales. And the idea is now, if you look at the top left, that all of the different scale names that are up there, that we can actually replace all of them with anger. And then the next one we can replace all of those with leadership, etc. Right?
Okay.
And yeah, we hope that as soon as we get to much higher performance with the trained models, that we can actually start to believe that relabeling, and we can literally make a realistic proposal of what a set of labels or constructs would be to capture the entire universe of at least IPIP personality items.
I have a question. I assume this is it's going that way, but is there also data from the actual responses to see if it reflects those correlations?
So would this answer it? So this is a comparison of the predictions of these models in terms of the scale similarities. So we have no responses of the link between the label name and the items. This is all done by the model, but we have validated these embeddings for the correlations in responses to the items in the different scales. And that's what you see here. So this is a big 5 data set, and we can show we can predict the correlations of 30 big 5 scales with an accuracy of R equal 0.54 currently. Again, this will go up quite a bit more.
Okay. Oh, so there are behavioral data in this.
Yeah. Oh, all of these are behavioral, right? I mean, internal consistency is behavioral.
Yeah, I knew that.
Yeah. And this is also behavior, but from here on, then it's just a prediction of the model.
Okay.
But yeah, so again, there's a larger data set. It's called the Springfield Community Data Set that has 1,000 different items. And that's what I'm currently training transformer models on. And then we will, like, this number will probably go up to about 0.8. So we'll reach a predictive accuracy that isn't far from the reliability of these scales, which leads to some very fascinating questions about what personality actually is, right? So why is it possible to predict responses to personality with that accuracy? And there's really 2 routes, and both are kind of interesting. One is that obviously personality expresses in text, right? So if you have a text about a person that's extroverted, you will see a different distribution of words than in a text that's about somebody who's introverted, right? And also a person who's extroverted will speak differently, etc. So there's a lot of good reasons why personality would express in text. But maybe the other pathway exists as well, and that is that we learn a representation of what personality is from our environment, and we use that representation, or that representation influences us when we render our responses in personality inventories, right? So it might also be that our own semantic representation of personality that we've learned from the environment is impacting our judgments, right? For instance, to try to appear more consistent, right? So if I answered, I like to go to parties, then I may also think that I don't know, I like to go to large friends gatherings, right? And that would be then an assessment based on me realizing that these two items are actually similar. And then I might be, due to a sort of a sense of consistency, might be motivated to answer the same way. So I realize the time is already fairly advanced. I wonder how to proceed with the at all proceed with the second project. How do you feel about it?
I'd say go for it. I mean, we have 18 minutes, I think, right?
Yeah.
Cool. Yep. I think that might be less. Might take a bit less time than the personality project. So yeah, so that's personality. In another project, we're interested in using language embeddings more as a predictive engine in order to figure out risk perception, and maybe use then the models that we train on data to figure out stuff like polarization, risk-related polarization, for instance, in media. So the starting point of this project is the psychometric approach. There's a very old literature that tries to understand how and why people assess the riskiness of risks out there. And the dominant approach that has emerged is a psychometric paradigm that one can understand as like a psychological feature engineering paradigm, is one where the field, and in particular Slovak and colleagues, have come up with a set of items that supposedly represent the important aspects of risks, such as, for instance, its dread, how new it is, how uncertain it is, etc. And that however we think about the risks in all these different dimensions is then how humans ultimately may think about the riskiness of a thing. Behaviorally, this has been established obviously by collecting data on both of these things. On the one hand, the different psychological features, and on the other hand, then the riskiness. So in a study, for instance, people might be prompted to evaluate the word robot or the risk robot, and then people would be answering on these different items along with an overall assessment of the riskiness. And then, yeah, and the same, people may do the same thing for virus. And yeah, there are two important conclusions from this. One is that the set of features can be further reduced to that framework of dread and uncertainty, so two-dimensional space, and also that these 9 items are pretty good at predicting riskiness. So we're talking about 75% of variance being explained of the ultimate riskiness judgment using these 9 different items of the psychometric framework. So in this project, we were curious of whether we can maybe do better than the 75% by using language embeddings. All of this work is typically done based on individual words or compounds, right? Or yeah, so it's a situation where we can easily pull the vectors for the different things that are evaluated, and then we can use these vectors as the input to a predictive model. Right, so we have then, it's exactly the same task, right? We have like virus or robot, etc. On the left, the judgments of the riskiness of these things on the left-hand side, and on the right-hand side, then we have 300 abstract variables that we plug into, for instance, a regularized regression model in order to learn weights of the different embeddings that optimally predict risk perception. And one reason why we believe that that we might actually be able to do well in predicting risk perception is some other work of ours where we looked at all sorts of different word norms. So over the last years, people have produced, or researchers have produced massive data sets of different word properties or psychological dimensions of words, such as balance or humor or tabooness or age of acquisition, etc. And in another project, we gathered all of those to see how well different types of embeddings are able to predict them. So here I'm contrasting with fast text and Glovi, which are 2 very popular word-based embeddings out there. And what you can see is that concerning emotional dimensions of words, SWO, which is the free association-based embedding, is doing quite a bit better at predicting these aspects of words than the text-based embeddings do. So the behavioral embedding from free association is doing quite a bit better than the text-based ones. And yeah, and we think there are reasons for that. I mean, free associations could be considered a more direct readout how people think about words. Text, on the other hand, has to obey certain constraints in terms of syntax or in terms of pragmatic rules of communication. So there are many reasons why behavior may actually be the better source for embeddings, even though we can't produce nearly the same amount of data from behavior, right? So here, these text-based embeddings, they're trained on orders of magnitudes more data than the behavior is, but the behavior produces better embeddings to out-of-sample predict emotional dimensions of words. So if we can predict emotion well, maybe we can also predict risk well. So that's what I'm showing you here. This is a reanalysis of data from a study from Sudeep Bhatia. He collected 300 risk sources, or roughly 300 risk sources, and he compared the first two models, the psychometric 9D, so these are the 9 psychometric items, and an older pre-trained versions of Word2Vec. And he found that, yeah, the psychometric items explain about 75% of the variance, and Word2Vec by itself is also doing pretty well, but not as well as the psychometric items. And an interest of ours was to see, hey, since then, a few years have passed and new embeddings have come up, FastText and Glovi, or at least new pre-trained embeddings trained on larger data. And also we were interested in seeing how well SWO, that is the behavioral embedding, is able to predict risk perception. And we can see the newer embeddings do quite a bit better than the somewhat older Word2Vec embedding. But we also see that the best embedding in order to predict risk perception is the behavior-based embeddings based on free associations. We can also see that that model alone is about as good as using these 9 psychometric dimensions. And what's really cool is that we can start to put these together, right? We can ask, hey, how good does the model having access to all of these dimensions is at predicting it? And for this data set, we see that we can improve the predictive accuracy by about 10 to 11 percentage points. What I don't have, we can also obviously just train or just use Glovi and SWO to predict it. And that's a little bit worse, I think, but I think it's still better than the psychometric. And these models, obviously, you can use in order to generalize again, because Glovi and SWO, we have embeddings for at least 12,000 different words. So we can use these embeddings then to predict the riskiness of any other word in the language or any text out there. We are right now actually in the process of collecting more data, a larger set of risks. And we find that the combined embeddings are now really pushing, with a larger data set, we're pushing beyond 90%. So we might be having a model that really is able to encapsulate all of the data, which also interestingly provides our opportunity to maybe probe these embeddings to figure out what are actually these other features that we need to ask people in order to figure out how they think about risks. Yeah, let's skip this one. And then the cool thing then is that when we just use these embeddings, that we can generalize to then predict the riskiness of text, or also the other dimensions. So we could also train on the uncertainty item in Slavic and then generalize that to any kind of text. And what I show you on the next 2 slides are just sort of proof of concept, where we use these models to see, hey, can we produce any patterns that kind of make sense? But ultimately, the goal is to take this further and maybe see we can predict, stuff like polarization. Yeah. So one example here is using the Hansard corpus, which is a large corpus, large historical corpus of UK parliamentary speeches. It has about 7 million speeches that go back to the year 1800. And we just ran our embedding-based risk perception model to predict the risk of these different speeches. And you can see some patterns. What we were looking for is particularly the two world wars. We wanted to see if we can detect anything there, and that seems to work rather well. There are also a bunch of other patterns that, not being an historian, we're not really sure how to interpret and whether that makes sense. We don't obviously we can't interpret all of these different peaks there just yet, but this is also done with the older data set, and we hope to have much more accuracy with the larger data set to predicting these things, and then maybe also the patterns become clearer. And what my doctoral student just did, which I think is more what we're interested in, is maybe also something that's interesting to you, is maybe see whether we can predict something like polarization in media. So here we used our embedding model to predict the riskiness of headlines for articles that have the word immigration as a function of different media sources for which ratings of their political bias is available. And as you can see, based on this analysis, is that media outlets that lean right tend to report about immigration in a way that, according to the model, is perceived as being more risky, right? Whereas then something, and that, for instance, that would be Fox News. And on the other hand, something that's more on the left-hand side, like the New Yorker, you can see is the opposite would be true. This is just a first attempt. We're trying to extend this, having more media outlets. We also want to do this with a larger data set, hoping that we get a little bit more accuracy. But our hope is to show that these models are then useful for things out there, such as, for instance, detecting how different outlets talk about different topics, societal topics. There was a question, I think, right?
Yeah, I think in the chat there was a question, but maybe it's more of the other work. So I don't know if you want to wrap up, and then we can go to the question section.
Yeah, I think I'm pretty much done. Yeah. So
well done.
Yeah. So this was two projects that try to leverage language embeddings to clarify the structure of personality and maybe to predict risk out there in the world. I hope I've convinced you that language embeddings are a really attractive tool. And I think there are many more things that can be done with these embeddings. And there obviously is already work out there that is using these embeddings for all sorts of things. But I think psychologists are only starting to understand really how much you can do with these embeddings. I think they're really powerful. Thank you again for having me, and I'm happy to stick around for questions.
Thanks, Dirk. That's great. Yes. Do you have access to the chat? Just curious, because Adam popped up.
I would, but I don't see my cursor. If somebody could tell me.
All right. Well, I can read out the question from Adam, who can't speak because he's on a train. And this relates to the first project. He says, your current performance of R equals 0.5 without training. He calls that a zero-shot learning method, which is what I would call it as well. Yeah. This essentially measures how your training corpora matches up to the item definitions of personality inventories. If you then use a deeper network and train it, you're no longer measuring the consistency of the language model corpora to the items. You're just learning a mapping from language model to the items. Have I got that right?
That sounds about right. There is a qualitative change in. So I would also, one can call it zero-shot learning, and then when we actually train it, I think there is a qualitative change in what these embeddings capture.
Okay, and can you refresh my memory as to what your feedback signal is in the training? I mean, when you say training, what is the criterion measure?
Yeah, so the criterion is correlations between items based on human responses. So there's a large data set that has human responses. I calculate the correlations between the items, and then I use a BERT model that's set up for predicting relatedness between things. And that one I train to optimize the prediction of the item correlations.
Which essentially means you add a regression layer or something like that, naively speaking, to the embeddings.
In principle, yes, but that type of retraining is able to change any parameter in the model. So you're not just learning, I mean, you could be doing that, you could just using them and learn weights. That's what we're doing in the risk project.
Yes.
But when we train the personality models, that's a type of training that can change any parameter in the model in order to capture, which I think is critical. So I was previously playing around with the universal sentence encoder and just doing that, just plugging them into a regularized regression and then predict. And that doesn't work nearly as well than using a transformer and allowing it to change anything in the model.
Okay, great, thank you. Other questions? I think we have 3 minutes technically. Was that?
I have a question
Can I
here.
ask a question or no?
Yeah, can you hear me?
Yeah.
Yes.
Yeah. So I was wondering if you had any, let's say, metrics or scores regarding the cross-domain aspect of the use of the embeddings. I'm thinking, for example, now if we consider these UK parliamentary speeches, like we could say, for example, that these embeddings were trained with some data maybe where the word war was not so often used. And I would assume that maybe in the past war was a concept more present in the speeches, for example. So it's like the terms are kind of shifting in the embeddings, right? So if you had any insights on that.
Yeah, it's that's a tricky issue. So that's one of the reasons why we're unsure whether to follow up on that historical analysis. It's just something that it's a data set that I recently had acquired and just did it out of curiosity. But historically, really, there exists the massive problem that the embedding obviously morphs through the ages. And there's some work that's also showing these problems. So there's been this work by Wulff and Lee, where they did LSA on different years or different decades of the Google Ngram corpus, and you can see that you get different solutions for the different years, which is just one indication of that there is something changing. So yeah, any historical prediction should always be taken with a bit of a grain of salt.
Okay. Yeah. It's quite a tricky problem, yes.
Yeah.
Okay, do we have any more questions? Right, so
there was something else in the chat, but I can't see it. I don't know.
No, we've dealt with the chat.
Adam just thanks Steve and thanks you for the presentation. So I'll take this opportunity to thank you for the presentation again. And yeah, and applause. It's applause. Right, so thank you. It was really a pleasure. And yeah, I'll see you everyone next week. Well, not next week, but afterwards, right?
Yeah. And thanks for doing that, Dirk. It was great.
Hey, thank you for having me. Looking forward to see you soon. Bye-bye.